Hi, Matt Cauthorn here, ExtraHop Networks. We're going to talk today about PAWS Dropped SYNs, what this counter is and what it means. All right. And I will tell you that this is a great example of some really sophisticated stuff that we bubble up in a trivial way. And, you know, it's videos like this that make me appreciate the solution quite a bit. I will share the sentiment of a coworker of mine, Eric Thomas. And he said something that was really insightful, I thought, and it runs like this. The network, TCP, I should say, is a great measure of how well the network is delivering your applications, but at the same time, it's also a great measure of how well the apps are using the network. So it's not just the network delivering the app, it's the apps using the network. And I will say that, at least to me, application delivery and true application performance management cannot live in isolation from the network nor the application itself. You have to address them both systematically. It's a discipline. Application delivery is a discipline, and you can't ignore one thing for the other. The traditional state of the art was the network team has their tools and the app team has their tools, and that's it. And there's this sort of organizational tension about what's the authoritative truth. And we don't do that. Our approach is to show you the full OSI stack all the way up to layer 7 and back again because it matters. So in the spirit of that comment, or soapbox, I apologize, PAWS dropped SYNs. Let's talk about why they matter. These are multi-second application stalls. Let's say you've got a business. Let's say you're selling ads, or let's say you're delivering videos or something like that, and you're wrapping sequence numbers. You're hitting this PAWS dropped SYN issue. And you've got multi-second stalls. You could be losing customers from that. I mean, when I say multi-second, I mean these are nasty stalls. So let's talk about what's going on here. Let's kind of deconstruct the issue a little bit. Let's say I have and this is very common, but let me get my tab out, sorry. This is very common in load-balanced environments, okay? And this is not, again, a comment on the efficacy of load balancers. They're super smart, great devices to have, solve lots of problems, but this is more of a deployment issue where it's easy to make a bad assumption about what defaults make sense and which ones don't, okay? So let's say we've got clients stick figure A and stick figure B out here, and we're going to simplify this as much as possible. Here's A, here's B. We've got a VIP side VLAN, public facing, and then we've got A in blue, private side VLAN. And back here are servers. And I'm going to do this guy in dots, say. I'm going to only focus on one of these servers in the pool for the sake of this discussion. So what's happening is that protection against wrap sequence numbers is that in high traffic environments, you're going to wrap sequence numbers. And so that RFC, they proposed the addition of a timestamp option, which helps sort of break the tie as to which sequence number, if you've wrapped, which one could be an old retransmitted segment or a new fresh sequence number that has just so happened to wrap all the way around. And you've got sort of ambiguous segments here. In the absence of timestamps, it'll corrupt the socket, actually. So you need that support. And so what we're going to talk about here is how it works in an LB, a load balanced environment. So let's say I'm client A, and I send a socket through. And what happens here at the load balancer is that he does source network address translation, or SNAT for short. And let's say that you've only got one IP in the address pool, 10.10.100. This is very common, .245. This is a very common setup. It works okay. Works okay in many cases, but in high volume environments, you shouldn't do it. I'll just go out on a limb and say that. You should not do this because it exposes you to too many nuanced problems, I'll say. And we're going to talk about one here. So in this guy, what he's going to do is he's going to translate the source address to this 100, 245 address. And so he receives, the server, when he receives this flow, is going to see the traffic sourced from the load balancer, the self IP address. Okay, and that in and of itself isn't bad. That works, it solves lots and lots of problems, great. But here's the rub. Let's say they talk, and I respond back to client A, and I send data, and then I send a fin, and I tear down the connection. This guy says, great, you do a successful four-way close, and client A is effectively out of the picture. Well, what's happening is the server goes into a state called time wait. time wait, time underscore wait. You can see this in netstat-an, by the way, on clients and servers alike. So he's going to go into the time wait state, and basically the idea here is that when you do a successful close, the sender of the final ACK, or the first fin, as the case might be, the sender of the final acknowledgement has no way to guarantee the delivery of that acknowledgement. So you don't know that client A received your final ACK. And so what happens is you wait around for 2 times the maximum segment to MSL, maximum segment lifetime. You wait around to reuse that socket until that timer has expired, and then it's a candidate for subsequent connections. That's the basic way it works. The same concept applies at the load balancer too, and that's the trick here. So the load balancer has a state table. They've got an idea of who's closed and who hasn't. And the load balancer is very, very, very likely to be doing kind of the right thing and trying to recycle time wait connections. You're gonna, if you Google around, you'll see lots of references to time wait recycle and time wait reuse, and that's what it's all about here, is recycling sockets that are in the time wait state, presuming a successful 4-way close, they can be reused. Here's the underbelly though, the dark underbelly. We'll do this in, I guess in pink to draw it out. So this guy now, let's assume this guy connects into the VIP. He gets it translated to the exact same source address and gets the exact same sequence number and source port, which is not uncommon. Remember, you know, if you're doing lots and lots of connections, these things are wrapping a lot. Okay, and the source port pool can saturate and all that kind of stuff. So using the same sequence number and the same port, and it hits the same server on the IP port destination, say port 80, IP and port 80. And it hits this socket, so it's the exact same socket definition that existed for A, except his timestamp will be different. Okay, and it could be way far in the past, it could be way far in the future, or it could be kind of close. And so what happens is this: when there's a timestamp delta, these timestamps are assumed to be a monotone, they call it a monotone, which basically means a regular tick forward in time, always moving forward. If I see this guy in the back and going backwards in time, and this guy B is going to connect with a SYN as he does to connect, I'm just going to drop this connection silently. That's a pause drop SYN. I'm in time wait. I hit the same sequence number, same source port, destination for the same server IP port combination. This guy's got a socket sitting idle in time wait. Common, and it's not, I don't know about very common, but definitely it will occur in load balance situations. I've seen it in the wild several times, you guys. Nasty multi-second stalls. That is a pause dropped SYN. Here's what to do about it. I hope that made sense. I know it's technical. It's a pretty technical discussion. Here's what to do about a pause drop SYN. If I can delete this, you add more. It's actually quite simple, and this is a best practice, at least to me. If you have a high volume, here's your load balancer. If you have a high volume site and you're going to have to do SNAT, a lot of people do. Sorry, I should not do it that way. I'm going to draw it this way. If you're going to SNAT, use multiple addresses. Address 1, 2, 3, N number of addresses, right? And so as you increase the SNAT pool addresses, you're going to find that there's a very low probability, statistically speaking, of running into this pause drop SYN problem, because you're adding all of those sequence numbers, all of those source ports, and it becomes very, very unlikely that you'll run into pause dropped SYN. And that's the end of the dropped SYN. That's the end of the video. I can't write and talk. Sorry about that. We'll see you next time. If you have questions, fire them over to forum.extrahop.com, and we look forward to hearing from you. Thanks again. Bye.